Hey everyone, and welcome back. Before you watch this walkthrough, make sure that you pause the video and try the problem yourself. Even a partial attempt will make the explanation that much more useful. These videos are meant to support your problem-solving process, not replace it. Across a lot of my practice problems, I highlight different aspects of how to approach, break down, and reason through problems. So you're going to get the best benefit by watching multiple walkthroughs rather than treating any single one of my videos as a template that you can copy. With that, let's get started. This practice problem centers around the merge sort algorithm, and the practice problem statement is honestly pretty straightforward. Implement a recursive merge sort for an integer array. We have input being just an integer array, and our output has it sorted from the smallest number to the largest number. In my last video, I walked through the reversal of a string, and more specifically, I added statements to the method that really highlighted what the runtime stack or the call stack was doing. This is incredibly important because there are some algorithms that are solved significantly simpler through the use of a stack. And whether that be one that we define ourselves or the runtime stack that Java has built in is honestly kind of irrelevant to the algorithm's success, not accounting for memory constraints, like running out of memory. While these types of algorithms can be implemented iteratively, meaning with loops, it's actually significantly simpler to implement them recursively and then just let those algorithms execute on the runtime stack. And that is merge sort. Merge sort is one of the most important examples of recursion because it shows what's known as the divide and conquer algorithm in action. And there's actually a whole suite of algorithms called the divide and conquer algorithms. Instead of sorting everything at once, we're going to repeatedly break the problem into smaller pieces. Let's start with identifying our base case. Imagine for a second what would be considered a pre-sorted small array. If an array has one element or 0 elements, no logic needed, we can say that it's sorted. So if the length is less than or equal to 1, we can just be done and say, cool, our list is totally sorted at this point. Now for the recursive idea. Recursively, what we want to do is split our list in half and recursively sort our left side and then recursively sort our right side. Once we've done that, we can merge these two sorted arrays together. Let's write all this in some comments. What I've done is I've already got my array set up here. I'm going to print out the original. I'll do my merge sort, and then after my sort, I can print it out again. Let's get that method written here. Public static void merge sort. We'll just call it, merge sort. And we're going to take in our array. For now, we're going to probably need to make some changes here, but that's where we're going to start. What we said was if our array is length 0 or 1, already sorted, there's nothing left to do. But if that's not the case, else we can split the array into a left and right half. We can recursively sort the left half. We can recursively sort the right half. And then once that's done, we can merge our two halves. Whoops, I don't know why that's in all capital. Merge our two halves together. All right, now let's turn each of these steps here into code. What we could write here is if the array is length 0 or 1, it's already sorted, we can just return. On a void method, this might look something like this. If the array.length is less than or equal to 1, return. If you know me, you know I actually really don't like this. I think this adds clutter to our code over other options. Because if I negate this statement, meaning if I say array length is strictly greater than 1, I can just put all the recursive stuff right in there. And the base case is just don't go into the if. And now I don't have like an empty if statement anymore. Some of that might just be preference, but I have a pretty strong preference for that. And if you're watching this video as part of my lecture series, for my courses, you need to do it this way and not have returns on void methods. Now we need to move into here to work our way through this recursive case. Next, it says split the array into a left and a right half. If you remember from our binary search video, this is really easy for us to do. We're going to take our array's length and we're going to just divide it in half, and we're going to get our midpoint. Once we've done that, we can make our left and our right side. Now, since right here we're really only doing this with integers that are primitives, they're immutable, we don't have to worry about deep copy and shallow copying individual items. Each item will automatically become a deep copy. So I can just say arrays.copy of range array 0 to mid, and that will get me the left side of the array. And then I can create the right side of the array with arrays.copy of range. Whoops, going from array. Oh, this should say array. Apologies. Catch all those. And this one starts at mid and should go to the end of the array. So array.length. There we go. So now we have our left and our right halves of our array. And now what we need to do is recursively sort each half of the array. So we will recursively sort the left by calling merge sort on it, and we will recursively sort the right. Now, I walk through what this really means and how this works in a different video as part of my Comp 1020 lecture series, where I actually show it with visuals and the call stack, and it becomes much more of a visual journey. But that's not going to happen here. This is more focused on the code. If you need more of that visual journey, please go check out that other video. Once you have done your merge sort on your left and your right half, and now we can merge our two halves together. Now, we can actually do this in place, but I think for ease, what I'm actually going to do is I'm going to create a new array, sorted array, and have my merge sort algorithm actually return my brand new array. So my sorted array, merge sort array, just like that. What this is going to allow me to do is make my merge algorithm just a little bit simpler. We can do my int array sorted, merge the left and the right into a single array, and we can return that sorted array. Now, the only thing we have to now consider is that when we call merge sort here and here, what does this sorted array represent? Well, when we call this sorted array on the left side, what we end up with is left being whatever we passed in, but now rearranged, and right being whatever we passed in, but now rearranged. Then we can get our sorted array and pass that all the way back up to the top. All right, last thing we need to do is write this merge. The merge function should be pretty straightforward. It is something you probably have seen before and hopefully did in an earlier course. So we take in our two arrays, left and right, and we're going to go ahead and create that new array. And we are going to merge the two sorted arrays into a single sorted array. And this is pretty straightforward. So first off, we need to create that new array that's going to be our sorted array. And our size of this array is going to be the size of the left side and the size of the right side together, since those are going to be all the elements in our newly sorted array. We're also going to need indices that keep track of the left side, the right side, and our sorted index. All of them, we can even say 0, 0, and 0. Each of these move independently from each other, so we do need all three. Now, the very first thing we're going to do is we're going to move along between left and right, moving them into the sorted array until one of these two become empty. So while my left array is less than my length and the right side index is less than the length of the right side, I can go ahead and figure out what needs to move into sorted. If the left side at the left index is less than the right side at the right index, I need the right brackets there, That means our left side is smaller, and that's what needs to move into our sorted array. So we can move into sorted with that position from the left side. If it's the other scenario, meaning greater than or equal to, then the right side must be smaller. So we need to do this, except we do it on the right-sided array. So we move the right-sided data point into sorted. And this continues until one of these two are empty. We've sort of processed all the elements in it, and the other one isn't. The next step is to determine which of those that is. So we can do this with two loops. We can say while the left side is less than the left dot length, dump everything in from the left side. So if there's anything left in that left index that we haven't yet processed, just dump it into that sorted array. If there's nothing, this loop doesn't run. And then we can do the exact same thing for the right side. Right and right. Once we've done that, we should have a completely sorted array. We can return it. And now we have merged two arrays into one. Let's go ahead and compile this. Oh, I just have the misnamed value there. There we go. Left and right. Make sure I did this right. Int array. Got to make sure I updated all my parameters when I made that change. Oh, and I am missing a return statement. Oh, I put this in the wrong place. Whoopsies. Right there, which also now means I'm going to need to declare this over here. Int array sorted can just start off as the array. There we go. So now in the base case scenario, I'll just straight up return my original array, meaning 0 or 1 elements. And in all other scenarios, I will go ahead and return my actually merged and sorted reference. Let's go ahead and compile that. Perfect. And let's run it. What? Oh, whoops, I forgot to change this to be printing my sorted array. Hopefully some of you at home caught that. Let's recompile and run that one more time. There we go. My original array is all jumbled up and my sorted array is in order. Now, if it helps you, we can do some more printing along the way. For example, we can print what the left array is right here. And we can do it actually right here. Left array, left pre-sorted, I guess, array, and then post-sorted array. And we could do the exact same thing for the right side if we also want to see what that might look like at each step. Right pre-sorted and right post-sorted. Now, if you go back to my previous video, you'll be able to see exactly what I did with the call stack and like numbering the different levels as the calls were happening. And you can do that here too if you're looking to sort of gain a deeper understanding of what is happening sort of under the Java hood. We can go ahead and do that. Let me just make this bigger so that we can go through it together. So what we see happening is the left pre-sorted array initially gets called on 835. Then this gets split in half and it gets called on just 8. This is a single value, meaning it's already sorted. So our code returns and we end up with the left post-sorted array just being 8. Now that we have finished processing the left side of this, we need to process the right side of this little mini subarray, which is 3 and 5. So this gets called recursively, where we pass in the 3, we realize that that's a single value and it's sorted. Then we do the right side of this little subarray and we do just 5. That is going to end up being sorted. And now the right post-sorted array is going to be 3 and 5. Now that we've done this entire side, we can go ahead and go all the way back up and recognize that we have now finished the left pre-sorted array. So we end up printing out our left post-sorted array of size 3, now being in the right order, because after each sort of set, we ended up doing that merge. We merged 8. Well, we merged 8 with nothing and just had 8. Then we merged the 3 and the 5 array into 3, 5. And then we merged the 8 and the 3, 5 array into 3, 5, 8. Once we have finished processing the original array's left side, we now need to go and do it to the right side. And it works exactly the same. We split it in half. First, we just do 1 and merge the 1 with itself and just get 1. Then we do the 9 and the 6. Each of those are individual. Then when they get merged back together, we end up with 6, 9. Then we merge 1, 6, 9 together right here. Now we have finished processing this array and turned it into this. We have finished processing this subarray and turned it into this. And now we can take those two post-sorted arrays and merge them together to get our final sorted array. It's honestly a little bit of magic, and I do recommend a visual sort of algorithm visualizer if you are struggling with this, whether it's one of my other videos or going to a website such as Visual Algo or even like a Python tutor website, so that you can actually walk through this algorithm step by step to get a really good understanding of sort of what this call stack looks like and why it does what it does. That's it, and now we've solved this problem. Now remember, you won't find my solution posted alongside this video. If you watch the walkthrough without first attempting the problem, stop here, close my solution, and try to write it yourself now. Post-walkthrough practice still counts. If you have questions about this problem or suggestions for future practice videos, please be sure to leave them in the comment section below. Thanks everyone, and I'll see you next time. Bye.